First of all, I would like to thank the organizers of this conference in this at this very nice place with all the blackboards, which I will use some of them. Sometimes I say I work in set theory without the axiom of choice, and I now realize this is not quite true, because the topic is that we construct models of ZF in which the axiom of choice heavily fails, but to construct these models we need the axiom of choice also heavily, and also the continuum hypothesis and some other results. So it's in fact, we work in set theory with the axiom of choice and build model for set theory without the axiom of choice. And all the results I present today are joint work with Saharon Celach, and the newer results concerning these four cardinals are joint work with Riccardo Platti, Salome Schumacher, and again Saharon Celach. The topic is between the relations, is about the relations between cardinals in ZF. So I will say first a few words about some basic facts about cardinals in ZF. So all our sets are assumed to be infinite, because if we have finite sets and we compare the cardinality, it's just finite combinatorics. So all the sets are infinite, and for an infinite set M, we denote the cardinality of M by some German type letters. This is the cardinality of M. And I have also to say that infinite means not finite, so this doesn't mean Dedekind infinite, it's just infinite is not finite. And we have the usual relations. Two cardinalities are equal if there exists a bijection from A to B, also between A and B, and then we say that the cardinality of A is less than or equal to the cardinality of B if there exists an injection from A into B, or we can say that there exists a bijection between A and the subset of B. And then we have the Cantor-Bernstein theorem, which can be also proved without using the axiom of choice. This means if we have an injection from the set A into set B, and we have an injection from B into the set A, then we have a bijection between the set A and the set B. So we can compare cardinalities by injections and bijections in ZF. And if you don't have the axiom of choice, it's not always the case that two cardinalities can be compared. So if you have two infinite sets, there may be that there is no injection from A into B and there is no injection from B into A. So then they are incomparable. On the other hand, one can show that the axiom of choice is equivalent to trichotomy, which means that if you have two infinite cardinals, M and N, then M is less than N, or M equals N, or M is bigger than N. So if any two cardinalities can be compared, then this is equivalent to the axiom of choice, and this is done by Hartogs. So on the other hand, if we don't have the axiom of choice, then there might be that two cardinalities are not comparable. Another equivalent form, so there are hundreds of equivalent forms, is that for infinite cardinalities, we have the cardinality of m equals the cardinality of m squared, where m squared is the cardinality of the set m times m. And this is done by Tarski. And this also tells us that if we have an infinite set, then we can, or under the axiom of choice, then it does not matter if we take the Cartesian product or if we consider the finite subsets of M, they all have the cardinality of M. But without the axiom of choice, it is quite different. So without the axiom of choice, it might be that this set is, this cardinality is strictly bigger. They cannot be incomparable because we have a natural injection from the elements into the ordered pairs. Now, there are some classical or old ZF results. There is not so much non-trivial we can show in ZF. So some of the ZF results are that in ZF we can prove that for an infinite set M, the cardinality of the finite subsets of M is always strictly smaller than the power set of M. So this is the cardinality of the power set of M. Of course, we have an injection from the finite subsets into the subsets. So we have definitely that it's less than or equal. But even without the axiom of choice, we always can show that there is never a bijection between the power set and the set of the finite sets. And another result is that if we consider finite sequences we can build from elements of M, we can distinguish between finite sequences with repetition and without repetition. The sequences without repetition I denote by sec11. So these are the injective sequences. And we compare them with the set of all sequences we can build. And we can compare these with the power set. And one can show that we have always that they are non-equal. So they don't have to be comparable, but there is never a bijection between the injective sequences and the power set or between the sequences and the power set.
Of what length you mean sequences?
Finite sequences, always finite sequences. So all these cardinals we consider are some, except this power set, are built by finite combinations of elements of M. And
sorry, just the two last ones also are not equal. You can prove that in the first one and the third one.
The first one and the third one, no. Okay. So they can be equal, but they are both different. And this leads to the following consistency results. So one consistency result would be, for example, so we don't have a bijection between the finite sets and the power set, but we have an injection. We can also have, consistently wise, a surjection from the finite set onto the power set. So we can have a surjection and an injection, but no bijection. And another consistency result is that we have sec, so the injective sequences, and we have the sequences. And of course, we have here that the sequences, injective sequences are less than or equal to sequences. And by this arrow, I mean that we have strictly less. So we can have that we have strictly less injective sequences than finite sequences at all. And then this power set, which is different to both, we can put here. It's the smallest of these three. We can put here, or we can put here. So this means that we have then more injective sequences than we have subsets. And two other results which we need later is A, that we can have less finite sequences than we have finite subsets. And the problem here is not only that we get this less than or equal, so we have really find a model of set F in which we find an infinite set M such that we can embed injectively the sequences with repetition into the finite sets, but not vice versa. And the result B, which is just a strengthening of this result, is that we have that there are strictly more unordered pairs than we have finite sequences with repetition, where this M2 is defined as the two-element sets, subsets of M. So for every sequence, we find injectively a two-element set, but not vice versa. And even with one element, we can build infinitely many sequences, finite sequences with repetition. So this is quite strong result, which we can show that it's consistent. So this also shows us that the axiom of choice, if things like this shouldn't happen, then we need some choice. So to convince somebody that the axiom of choice should be true, one can say what happens if it fails. And let me now I can use the other part. Let me now introduce the four cardinals we consider. So we consider the set of finite subsets, the set of two-element subsets, set of injective sequences, and the set of ordered pairs. So what we have by set F is we have an injection from here into here. So this is bigger than or equal to this one, and you have an injection from here to here. And now we can ask, also this is kind of a diagram. It's like the Chichon diagram. So you have some cardinalities, and then you say what are the possible relations between them. and there are some restriction. In the Gichon diagram, you have B is less than or equal to D, and then you like to separate them. And we do, in fact, the same as here. But in addition, we have to require that to compare them, that they are comparable. So we assume these four cardinals are pairwise comparable. And we also assume that they are pairwise distinct. If they are pairwise distinct, then this set has to be bigger, the finite sets, than the two-element sets, and the injective sequences have to be bigger than the two-element, the ordered pairs. And now we can ask how can we move them now? So what kind of relations we have between these two, for example, or these two. And this is also like the Gichon diagram. If you have the cardinal characteristics and you assume the continuum hypothesis, then it's equal. And also here, if you assume the axiom of choice, then all these cardinals are equal to the cardinality of M. So if we don't have the axiom of choice, then we can move them, and these are the only restrictions. And we can then see what we get. So we have, so this is the basic diagram, and then we can have, I just draw these 4 points. Then we can have an arrow from here to here. And of course, we also get, because it's transitive, this linear ordering, we also have an arrow from here to here and from here to here. But I just draw these 3 arrows which are essential. Then something else we get. So this is, I call the N diagram. Take this away again. And then we get a C diagram. And we have a Z. And there are 3 more. We have the reverse N. We have kind of reverse C. And we have a reverse Z. So this. Huh?
I don't understand your diagram. What in the C? Which cardinal is which, for example?
Still this one. So this is squared, the ordered pairs. You have less ordered pairs than you have unordered pairs, two-element sets, and you have less than finite, and you have less finite set than injective sequences. And probably you see which one would be the most natural.
None of them are natural.
None of them. Yeah, this one.
Oh, the reverse.
The reverse, because if the cardinal is finite, for finite cardinals you have less unordered pairs than you have ordered pairs. You have less ordered pairs than you have finite. If the set has 20 elements, then you get this reverse set. And the problem is that this construct a model in which this holds also for infinite cardinals. Another question is how we build models of ZF in which such diagrams can hold. And the construction is with permutation models. If we have a model of ZF, it looks like this. This is V model of ZF. And we can ask if there are some automorphisms, some non-trivial automorphisms. And the non-trivial automorphism has to move this the empty set to the empty set. So this model is rigid, so you don't have any non-trivial automorphisms. So if we like to have automorphisms, we have to replace this empty set by a set of so-called atoms A. And the atoms, these are sets which do not have any elements, but which are distinct from the empty set. So these are also called Ur-elements, so yeah, or atoms. And then we build, like for ZF or ZFC, we build step by step power sets. And then we have the power set of the power set of the atoms, and so on. And at the end, we get, if you start doing this in ZFC, we get a model of model M, which is a model of ZFA, also ZF with atoms, plus the axiom of choice. So we first assume that we have the axiom of choice in this model of ZFA. And then what we do is we introduce a group, so a set G, which is a filter, so-called filter of subgroups of the automorphism group of the atoms. And these subgroups we usually call F. So we have a certain set of subgroups of the automorphism group of A. And then together with this filter, we can define what does it mean that the set X, which appears here, is symmetric. And we say a set X is symmetric if we find a subgroup F in our filter, such that if we apply all the permutations in F to the set X, then it moves X to X. And X is hereditarily symmetric if not only X is symmetric, but also all its elements. And then there are also sets in here which are not hereditarily symmetric, and these sets we just cancel. So we take the model, so the submodel of this M, of all hereditarily symmetric sets. So because we cancel some sets, we lose the axiom of choice. So eventually we get a model V, which is a model of ZFA plus non-AC. And this model we can then embed with the Yerkes-Sochor embedding theorem into a well-founded model in such a way that if we consider an initial part of our model V, then it is mapped such that all statements which hold in here also hold in here in this well-founded model. So to obtain a model in which the axiom of choice fails, we start with the axiom of choice, build such a permutation model. In fact, we build this filter of subgroups of the automorphism group. And then we can, if we can show that, for example, and this would be the case for these diagrams, we take M as the cardinality of the set A of atoms in here. And if we can show that these relations hold in this permutation model, then we have found a model after the embedding of set F in which these relations hold. Now, going back to this diagram, the diagrams. So this is the most natural one. So we agreed, I think, no. More or less. This is true in the Mostovsky model. In the ordered Mostovsky model, so A is isomorphic to Q. So we have the set of atoms are in fact a dense linearly ordered set. The permutations are permutations which respect the ordering. And the filter is generated by fixing finitely many elements. So we can fix finitely many elements and then consider all the permutations with respect to the ordering, order-preserving permutations. And then we get a model in which we have quite a lot of choice, because finite sets, they are finite sets of atoms in Q. They have a minimal element, so we have a choice function. So we have quite a lot of choice, and this behaves like then finite sets. And for these two models, they are essentially the same models as for A and B. Here the atoms are built step by step. So we first have a countable infinite set, and then we build sequences of these atoms. And for two sequences, we have two copies, one with 0 and one with 1. And this gives us a 2-element set of atoms. But inside, there are this coding of the sequences. And we build them step by step, and then we get the diagram N or C. So one of the problem is not only to have the crucial steps. So here, for example, this one is crucial, and this one. The other ones are quite easy to get. The problem is always that we don't have an injection in the wrong direction. So we have not only to show that there is an injection, we also have to show that there is no injection in the other side. And this was also the main problem for N and Z. For N and Z, the models or the set of atoms are the elements of a domain of a model of size continuum. We also assume the continuum hypothesis, and it's Aleph 1 universal. This means that every countable model of our theory, and the theory is just having an injection from one of these sets into another. So every countable model appears infinitely many often, and it's also Aleph 1 homogeneous, that if we have two countable models which are isomorphic, then this isomorphism can be extended to an automorphism of the entire diagram. And then there is a third property, which is a technical property, which allows us then to show that there are really no injections in the wrong side. So these are the new models for N and Z. And this diagram C, this is still open, if this is consistent. Because the problem is that we have here injection from ordered into unordered, and here from unordered objects into ordered again, and this makes it plausible that there is also, if we have these two injections, that we also have an injection from the injective sequences into the finite sets. But we can not prove, we couldn't find the model, and we cannot show that it's inconsistent. So that was all. I thank you for your attention.